You're listening to The Fire Break with Steve Wolf.
Welcome back to The Fire Break. I'm Steve Wolf. As you know, The Fire Break is sponsored by Team Wildfire, developing innovative solutions for wildfire suppression, mitigation, containment, and anything else you want to do to a fire. I have got with me a fascinating guest today, Abraham Zhiri. He is a researcher from Africa who's currently working in Cambridge, not Cambridge, Mass, but Cambridge, England, doing a lot of very fascinating research, particularly as it applies to fluid dynamics and the study of fluid dynamics' role in predicting the movement of wildfire. So that's, of course, fascinating to me. Welcome to the show, Abraham. How are you today?
Thank you so much, Steve. I'm fine and I'm good. And how are you over there too?
We're good here as well.
Nice.
So how did you come to be in England?
Okay. My journey to England happens to be what I can say a miracle by God, because England was a least place I have in my mind to go for further studies. But as God will have it, I just make an application to Cambridge, and at the first shot, based on my research and work so far, I was lucky to be part of those shortlisted for the admission, and also got a scholarship by MasterCard to be in Cambridge to study for 1 year MPhil in scientific computing. And that's a summary of how I found myself in Cambridge.
Fascinating journey, right?
Yeah.
Where did you grow up?
I grew up in Nigeria, specifically in Niger State, a state in Nigeria in the middle belt of Nigeria, with the capital, Minna. So I was born and brought up in Bida, a small town close to Minna, like just 2 hours away from Minna. I was born and brought up in Bida, but I currently live in Minna, where I work with FUT Minna and also as a researcher at the same institute.
I see. So you've got a lot of experience in that institute, and now you find yourself in Cambridge, England. Tell me about the research that you're doing there.
Okay. Currently, I am working on the study of detonation in reactive gases, and the modeling of diffuse. The study of detonation waves.
Okay.
Detonation waves in reactive gases, and also the study of lightning and strikes that leads to detonation as well, using diffuse interface method or the study of multi-phase fluid method. And primarily, we model the simulation using C++ program, and we try to see how different equation of states will be used to model the interaction between two or different materials and what the resulting outcome will be, basically.
Okay. And what do you see as the long-term practical application of this knowledge?
Okay. The practical application of this knowledge is very vast, because a lot of things happen as a result of interaction between each other. Like, for instance, when you talk of fluid dynamics, in fluid dynamics, you're automatically talking about liquid, you're talking about gas, you're talking about plasma, you're talking about even solid. So we try to see how a liquid and a gas, for instance, can interact with each other and then share some properties like pressure, like density, and how it can translate or transit from one position to another. Especially when you are modeling water with a gas, they have different densities entirely, and the pressure drop has significant difference. So we try to model how this interaction will be smooth and see the behavior of these properties entirely.
Okay, so you're looking at the way different gases interact, and you're trying to model what happens when they detonate or when they react with each other. I presume that this is how a single gas interacts with oxygen, or multiple gases interact with oxygen to get that detonation. And of course, you have some detonations that occur without oxygen, right?
Yeah.
Where you have an oxide in the mix already.
Yeah.
So, how fragile is the detonation reaction. And I'm asking this because, we know that there's thousands of lightning strikes every day that start wildfires, right? And when we look at a fire like, ooh, big scary fire, but when you actually look at the level that you're looking at, where the fuels are combining with oxygen, or where there's a detonation, I imagine that reaction is fragile and requires just the right conditions in order to proceed with that reaction. And so I'm wondering if any of the research you're doing might lead to ways that we could disrupt that reaction, which we call fire suppression. But,
Yeah.
the fire suppression is really at the macro level. What happens, at the micro level with that fire reaction? And are you discovering things that might help us to disrupt that?
Okay. Right before my coming to Cambridge, I actually have interest in how wildfire spread can be suppressed and how wildfires. Can you hear me?
Yes, now it's better.
Can you hear me very well?
Yes.
Okay. Probably before my arrival in Cambridge, I have this interest in seeing how wildfire spread can be suppressed or can be managed, because the obvious truth is that we cannot stop the ignition of wildfire. It's a natural occurrence, and it's also human induced. But natural occurrence can occur at any given point in time if any of these three elements of fire triangle are present, which is the fuel, which is the oxygen, and which is the heat, which is the temperature. So now, talking about how to find measures to mitigate against fire suppression, against fire spread, or to control the suppression, we try to look at what actually makes forest or a vegetation to be susceptible to ignition. That's the first step. Now, before ignition can occur, there must be availability of fuel, there must be availability of oxygen that supports combustion, and then there must be heat. These three things must be present before fire can ignite. And once these three things are available, then there will be a strike, there will be an ignition, and then later it will transmit to detonation. So we try to see how we can alter any of this to prevent ignition of fire that will lead to combustion, that will lead to fire spread as a whole. And out of all these three, the physical ones that we can actually lay our hands on is the what we call CFM, the combustible forest material, which happens to be in three phases. We have the volume fraction of dry organic substance, we have the volume fraction of moisture, and we have the volume fraction of coke, which is the soil pyrolysis. Now, if any of these three is not available, meaning there won't be ignition in the first place, because the heat and the oxygen both cannot ignite fire, because there must be a fuel that can actually catch or hold the fire. Now, in a situation where a forest, or let me say a bush, is very dry, susceptible to catching fire, it has or it harbors long-time drought, there is intensive heat, then such place is susceptible to catching fire. So mathematically, we try to model some mathematical equations based on this natural occurrence or phenomenon to see how property like temperature, property like oxygen can be modeled or can be varied to reduce the tension of a forest catching fire, or to reduce the rate at which we have susceptible forest vegetation, which is the volume fraction of dry organic substance. Because it is obvious that if your forest is very dry, it can easily catch fire, compared to a forest that has moisture content in it. Like a fresh forest that is not dry will not catch fire as a dry forest. So
Sure.
talking about detonation aspect, detonation will happen when there is high activation energy, which happens to do with raising the temperature and automatically raising the pressure. And then it will now reduce the induction time and thereby accelerating the rate at which the events will occur and then transmit to detonation.
I see. And tell me how you define detonation. It says, when I worked in explosives, a detonation is a particular type of reaction that proceeds, faster than the speed of sound.
So
Are you using the same definition for detonation?
yeah, detonation, to my little understanding, is the outcome of ignition induction, and this depends on how fast the activation is, or the heat released during the induction phase. It depends on these two factors. If these two factors are very high, then there's probability of detonation occurring very fast. But if these factors are very low, then detonation may not occur on time, and then the induction phase will take a long time.
I see. Now, I had been taught that it wasn't just the fire triangle, right, of fuel, oxygen, and heat, but that you
Yeah,
also needed that fourth component of the chemical reaction, where the fuel
yeah,
and the oxygen interact they
yeah,
are and then there are new products of the reaction, right? So
yeah.
is it possible that you can have fuel, oxygen, and heat without having fire because something has interrupted the chemical reaction process?
Yeah, very possible.
And
Very
what
possible. Okay, and I
so
will explain in this manner. Like, for instance, as I've said in the past, you have fuel, you have oxygen, and you have heat. Now, these are the three basic equations of wildfire spread. Now, oxygen stand on its own, temperature, which is the heat, on its own. Then this volume fraction has three sub-equations. Now, these three sub-equations of fuel can be dry organic substance, it can be moisture content of the forest aspect, it can be pyrolysis, partially burnt trees, or partially burnt fuel somehow, not fully burnt, not ashes, but not fresh. So
okay,
if these two are present, the volume fraction of dry organic substance and coke are present, then there will be fire or there will be ignition. Very possible, because once there is heat and there is oxygen to blow it, it will catch. But where you have just volume fraction of moisture, for instance, the forest is just fresh, there is no dry organic substance in it, there is no partially burnt tree or anything in it, then it will be very difficult for that forest to catch fire or for ignition to take place. And that's why even the forest firefighters, what they use primarily to combat fire is water. Yeah,
and are they using that water? So the water could be used for several purposes, right? The water could block the fuels from oxygen physically, right?
yeah,
Creates a barrier between the fuel and the oxygen. The water
yeah,
can be used to remove heat, either direct conduction as the water touches the fuel, or with
yeah,
evaporative cooling. And then the
yeah,
water can also increase the relative humidity as it evaporates. So
exactly.
no matter which one of those it's doing, it's helping you put out the fire.
Yeah,
Okay. And it's the most readily available thing that we have to work with.
yes, yes.
Yeah. Okay. So to what degree does the relative humidity play a factor in ignition?
Pardon?
The humidity, the amount of water in the air, to what degree does that impact the likelihood of the reaction of pyrolysis or the spread of it?
I will say that the higher the humidity, like the higher the water content or the moisture content, the lower the level of fire spread, or the lower the rate of ignition.
Okay.
And currently, I'm trying to look at the equation of moisture, the volume fraction of moisture, to see how convention and diffusion could be incorporated into this equation, to see how the fluid is being transported around the moisture in the presence of wildfire spread, or in the presence of ignition, mathematically. So I'm working on that currently as one of my research.
How's that going?
It's going well. It's going well.
What are the challenges there?
Um, the major challenges I face as a person, let me be personal, is the fact that at times when we do some research, and at the end of the day we have probably got some findings theoretically, I love to see how it will be implemented practically, for me to see that, okay, this thing that works on a paper or that works on computer program and gives results, actually has been implemented, and then this is the reality of it.
I see.
So
Nice.
what I try to do is to, okay, let me incorporate diffusion term and convection term into volume fraction of moisture, because out of these three equations for the combustible forest materials, the only thing we have to hold in the three of them is the moisture. That's our weapon to combat the fire. So let's see how we can incorporate diffusion and convection into this equation, and then let's establish the fact that it will give us a unique solution by testing the existence and uniqueness of the model entirely. So I'm currently working on it, and it's going well for now. It's going well.
So do you have like concurrent tracks of research sometimes where you're working with formulas and computer modeling, and that's telling you this is what we expect would happen? And then do you do physical trials where you can put those mathematical theories to the test?
Sincerely, for physical trials, that is what I have not done actually from my research, because my research is more of theoretical. If not that I'm in Cambridge now, back in Nigeria, we do most of our work on paper and then with a little aspect of simulation, because virtually most of my work on fire spread has been on analytical basis, or let me just say semi-analytical. And then at the end of the day, I try to vary my equations or my solutions using Maple software to see their behavior graphically, and then I draw conclusions from their from the graphical outputs. Rather, I draw conclusion. For instance, when I increase the radiation parameter, what happens to the temperature equation? What happens to the moisture equation? What happens to the volume fraction? If temperature is increased, will the volume fraction of coke increase or decrease? Something like that. And then I draw conclusions from my findings based on what I see from my computer simulation. But actually, I have not been able to practically implement some of these models to see them.
I see. So is there any way that you can compare the theoretical results that you get with actual results from wildfires? Are you able to look at the conditions in a particular area and make a theoretical assessment of what will happen? And then when it burns, you compare what happened to what you thought would happen.
Yeah, with the fact that I'm in Cambridge now, that is one area I'm trying to look at into the future to see how to actually, like a form of validation, validating your results from what has been established based on experimental results or maybe some numerical results established before yours. And that is one area I'm trying to work on now as I'm in Cambridge, to see how I can validate my models with the existing models with their respective results, being it numerical or experimental.
I see. And what kind of support do you have at the university? Is the research that you're doing very popular? A lot of people are interested in it, and they give you a lot of support, or is it just, oh, Abraham doing his own crazy thing again?
Currently, I will say that my research at Cambridge for now is not actually based on wildfire stuff for now, because I was actually working on wildfire before I came to Cambridge, and right now what I work most on is shock ignition and transition to detonation, and diffuse interface model simulation using different equation of state. So I'm trusting God that by the end of my MPhil program, from the experience I will get from this MPhil course, I should be able to integrate the skills acquired from this study of detonation and explosive gases into wildfire spread, to see how I can marry the two together and then improve what I've learned so far, or what I've done so far on wildfire spread. And also based on what you said the other time, to see how I can actually validate my outcome or the result of my simulations with the experimental one or the ones that have been existing in the past. So that's one area I already note down to work on after my MPhil here, to improve what I've been doing before I came here on wildfire spread studies.
I see. And currently, what do you think are the most valuable predictors of wildfire spread?
Let me
Like
get the question
a
right.
fire starts and we want to know in 2 hours, where's this fire going to be? Good question, right?
Okay.
Legitimate question. So what do you think right now are the best ways to go about that of existing software?
For now, as I've said, I can't really say much on that because I've not been exposed to plenty of wildfire spread software. There is one that I was trying to study before I came here. Um, um, FD, is it fire dynamics something?
Yes,
It's fire dynamics simulator. Is it FDS?
I think so.
There's a software I was trying to study before I came to Cambridge about how to predict and simulate wildfire spread to know the direction it will go and how long it will travel. But sincerely, I've not been able to have a glimpse of what I'm supposed to know on that before I came to Cambridge.
I
And
see.
once as at the time I arrived there, the whole scenario just for the meantime is not as having full time to go into the study as I would have done if I'm not here. So I'm still thinking about that to see how actually, in fact, there was a work I was doing before now that mathematical modeling of predicting wildfire spread to predict the fire on how it can travel, how long it can travel, and at what extent it can travel. If it occurs, for instance, from a point A to point B, that's one. Also, I was trying to look into it depends on on the nature of the fire. Some fires can be finite, some can be infinite. So how do we determine it mathematically? By setting some boundary conditions for them? Because some boundary conditions will have to be finite, some will be infinite, some will be Dirichlet, some will be Newman. So how do you determine all of this in trying to predict the spread of wildfire?
So to give me
So
an example of what would be an infinite factor.
for instance, being human, you have a forest before you, and the forest has already caught a fire. And with your physical eyes, you look at the extent at which this fire will burn from where you are standing, and you can't even see the end of the forest as at the point where you are standing. You can assume it to be infinite. But for instance, you are standing at point a forest caught fire, and then you are looking at point B where the fire will actually stop. That after that point B, there is no more grasses or bushes or anything that can catch fire. Then that is finite. So you can easily set boundary for it because
I
it is
see.
measurable. And since it is measurable, then it is finite. Then you can easily determine that boundary condition. Also, it can happen. It can happen that, okay, from point A to point B, there are grasses, but after point B, there are no more grasses, no more fuel to burn. But it's possible that after some little distance, there comes another forest that is very susceptible. In the presence of wind, that can be, there will be what we call spotting fire. The wind
Yeah.
can just escalate one of the firebrand from where it is burning to another forest somewhere. And then
Yeah.
before you know it, the fire continues. So that again will have to be based on another kind of model or boundary conditions, if I may say.
Yes.
So
Okay, that's very interesting. And firebrands, or what they call embers in some places, cause enormous spotting at great distance, right? Sometimes much further away than people would expect,
yeah,
right? We see sometimes spotting 100 kilometers away.
yeah.
And so have you studied at all what some of the actual conditions are that you then have to go back and model? How would you explain from a fluid dynamics standpoint, 100-kilometer spotting?
Let me get the question right again.
Yeah. So let's say that there's a phenomena that happens, right? You've
Okay,
observed this phenomena in the real world, right? 100,
okay,
100-kilometer spotting. So then to inform your model, you have to tell your model this happens in real life, right? So the answer
okay,
has to include this possibility because it
okay,
is real. And then you go
okay.
back and then you have to figure out the fluid dynamics of how that firebrand got from here to there.
It,
Do you have to
if
do
I
that?
get it, if I get you right, like talking about how firebrand escalates fire from one place to another.
Yes, that's right. We know that
Okay,
happens, right?
yeah, it happens.
Right. So how would you model that?
Well, I think in that situation, there'll have to be like another set of equation outside these 5 basic equations.
Yes.
Because
Okay.
these 5 basic equations, once there is a fire and it has ignite and it is burning, these 5 equations must come to play because it can't burn without heat, it can't spread without oxygen, and it can't burn without having susceptible forest material, either any of the 3. Even the one with moisture can actually burn, but at a very slow rate with a very high temperature before it can start burning. Or the temperature will have to get the moisture content dried off before it can start burning. So this is constant. Now, talking about the spotting fire or the firebrand traveling, there will have to be another set of equation. And that set of equation will also, it will take the form of, how do I put it? It will have to take the form of differential equation, which will also be like a partial differential equation because we'll have to calculate the distance it traveled from where it was burning to another place with respect to time. And then we'll have to capture that thing, the firebrand itself is a property that need to be represented. So it has to come into the model equation. And then I think there should be a diffusion term inside that equation because diffusion occurs in 3 states of matter: solid, liquid, and gas. And being transported from one point to another comes through gas or oxygen that blows to take it from one point to another. So
Yes.
I think these are the major variables that will come into play to give us another set of equations. So everything will not be like 6 equations to account for the firebrand that helps in transporting the fire from one point to another.
Okay. And then the diminishing transport percentage, right? At 1 meter from the source of the firebrand, 100% of the firebrand, right, goes 1 meter. But maybe at 200 meters, only 80% of the firebrands make it that far, right? Because of their flight characteristics, they fall to the ground. And then maybe just some smaller percentage, makes it 100 kilometers. Right. So
Yeah.
the likelihood of a spotting fire would be relative to the distance from the firebrand source. Do we know anything about what pyrolysis conditions generate firebrands or embers more than others? Does it have to do with the moisture content in the wood, or what are the factors that contribute to firebrand formation?
Factors that contribute to firebrand formation. Okay, a firebrand is that substance that transports fire from one point to another, right?
Yes.
If I'm correct. Okay.
Right.
Now, factors that contribute to a firebrand formation. Number one, it could be as a result of wind. When there's a strong wind will by default transport fire from one point to another using the pyrolysis product, because pyrolysis products cannot burn instantly and turn to ashes and diminish. So it will still carry some content of fire within it. It's not fully burnt, but it's still having fire in it. So going to another place, it will actually go and kickstart another form of fire. That's one. Then 2, it could happen that probably in those bushes, there are some wild animals in those bushes. And then as a result of the fire, these wild animals probably caught a fire, and in the process of trying to escape, fire can follow their entire being to another fresh forest, and then fire will kickstart.
So an animal can be a firebrand.
Yeah, it can be.
That's a horrible idea.
It's just from my thinking, because, for instance, some animals don't die instantly when they caught fire. Some that has plenty feathers, maybe part of the feather has caught a fire and then trying to escape to another place for survival.
Yes.
Fire can just like, and some forests at the smell of heat, it can just ignite fire. Once they're already susceptible, temperature in that region is already high, the environment is already very dry, and then there comes a sense of heat, just like petrol to the smoke, like the gas from a petrol
The
tank,
vapor. Yeah.
a vapor with a smell of heat, it will just come together and explode with fire. So something like that can happen. That's from my own perspective,
Wow, that's
which can give
fascinating
us another
idea.
model.
You haven't modeled that yet, right? I see. So what are the areas of research, that you're working on that you think are most likely to become, a product or a method or a technique for suppression or containment of fire?
Okay, having known that wildfire spread is caused as a result of two major things: natural induced action and by human activities. Now, by human activities, it contributes also to climate change, and climate change also contributes back to starting wildfire, and wildfire also contributes back to climate change. So now, this wildfire could impact the atmosphere negatively, and the atmosphere or the change in climate could also impact wildfire spread negatively. In a region that has high temperature naturally, those regions have more dry lands, have more susceptible forest materials that can catch fire. Now, talking about wildfire spread model, having this type of model, it would be very necessary or important to look at the influence of wildfire spread in climate change. Also, this wildfire spread, there are instances where, like, I don't know, but from my country, from my country in Nigeria, when we talk of oil and gas, transportation of petroleum, petrol is not just transported by trucks alone, it is transported by pipes buried beneath the earth that travel for a long distance through some thick and dry forest. Now, it could happen that wildfire can start anywhere. What happens when there is a wildfire in the presence of these pipes passing through where there is fire? It can again further amplify the devastating effect of that fire in that region and cause destruction to these pipes, cause pollution to the soil, cause pollution to the atmosphere. If there is a nearby water, also cause pollution to the water. So this wildfire spread model can also be looked into in the aspect of its impact on oil and gas. I don't know, like its impact on fuel pipes buried beneath the earth. And
Yeah.
talking about fuel pipes, it's also fluid dynamics because fluid is being transported through those pipes.
And then
So
when you heat
it
them
can
up,
give birth to another model.
yeah. So there's a lot of depressing things can happen out there.
Yeah.
Yeah. So, but you smile a lot, I see. So I guess the devastating effects of the things that you describe haven't affected your mood.
I'm happy when I discover a problem and then try to get a way to solve the solution, to find solution to it. Because identifying a problem is the first step to solve the problem. If you don't identify a problem, then there is nothing to solve. So when you identify a problem, then you start thinking on how to put things together to get solution out of it.
Yeah. And so what you're doing is really, you're taking a problem that's something you could physically observe, and then you're expressing that problem mathematically.
Yeah.
And then when you express it mathematically, then you can break it down and go about different ways to solve it.
Yes.
Very interesting. Very interesting.
Yes.
Wow.
Yeah.
So are you optimistic about the future of being able to minimize the devastation of wildfire?
Hello. Hello.
Yeah,
Sorry,
can you hear
I
me?
wasn't. Yeah, I can hear you now.
Okay. Yes. So wildfires, we all agree there will always be wildfires, but
Yeah.
wildfire devastation, there does not have to be. Right. We can build homes out of things that are not fuel. Right. And
Sorry,
we can.
your voice is breaking. I can't hear you.
Oh, okay. Can you hear me now?
Yeah, I can. Yeah.
Okay. So I say there will always be wildfires, but there does
Yes.
not always have to be wildfire devastation of the built environment.
Yeah.
And so how do you feel like your research will be used to minimize, devastation and losses from wildfires?
Hey, let me talk from theoretical point of view
Yes.
based on what I've done in the past.
Yes.
In the past, I worked on Wi-Fi spread and I solved it analytically. And from my analytical results, I used the Dirichlet boundary condition. And then the best thing that can help in suppressing Wi-Fi spread is quick removal of heat from a burning scene. And the quick removal of heat must come with something that is opposite heat, like there is hot, then come with something that is very cold to mitigate the situation. So from my simulation, we varied this parameter, radiation parameter. We got that parameter from the mathematical model we formulated and from the analysis we did after we have non-dimensionalized everything. We got radiation parameter, and when we varied the radiation parameter, increasing the radiation parameter, it was decreasing the temperature of the medium. So the more the temperature decreases, the more the environment becomes calm, and then the more fire will be suppressed. So radiation parameter is one key thing that should be controlled or that should be used to fight fire. But again, it depends on, as I've said in the past, it depends on the boundary conditions you set. If it is Dirichlet or Newman, because both has their own effects.
So let me make sure I understand. You're saying that of the factors that contribute to wildfire spread, the thing that you could do that have the most impact on reducing fire spread and enhancing suppression efforts would be removing the heat. Because you can't remove the oxygen.
You can't remove the oxygen, obviously.
Although that's not entirely true, right? Because when you spray mist on a fire, small water particles, and they evaporate and turn into steam, the steam displaces oxygen.
Wow.
Right. So,
yeah.
So if things aren't crazy windy, then you can actually displace the oxygen with the steam, because then oxygen becomes a smaller percentage of the gas in the environment around the fire. Wow.
That's a good one.
Yeah.
Yeah.
Well, that's right. So it looks like, water really is. So in places where there's not a lot of water, I'm guessing across the equatorial area of Africa, when I look on my Aurora Tech satellite map of fires, I always see, a big band of fire right across the middle of Africa. And I imagine that there's a scarcity of water as well. If there were more water, the forest would be green and it wouldn't burn so much, right?
Yeah.
And then, so what happens? How do you have to plan a community in an area where you cannot count on water for suppression?
I've actually thought of that in the past, and I will start in this way. We have two types of fire generally. We have the domestic fire and we have the wildfire. So the domestic fire tends to have more control measures than wildfire. Reason being that the impact of domestic fire is easily felt. Like when a fire outbreak occurs in a building, people live in building, and then people you see that the rate at which the suppression rate will come will be faster than when it is inside the bush. So I was like, part of the control measures for fighting domestic fire is this thing they put on the building is it strike absorber? Something, is it thunder absorber that stops some ignition from occurring, for instance?
Yes.
So now I was like thinking in this way, though I'm not an engineer, but I was just thinking through that area that is it possible to have like some device, or just the way we have some strike absorbing device planted in our homes or in some big buildings? Is it possible to do something like that in a reserve forest that is well dedicated for some purposes, in a place where there is not like easy access to water, should in case wildfire spread occur, that device can just absorb the ignition that is about to take place for that particular environment and suppress the spread of the ignition. I
So,
have that thought, but I don't know how to go about it. I don't know how to like create a model for that, or come about something that will serve as a strike absorbing device that can absorb thunderstorm or lightning or ignition trying to take place naturally in such places.
well, on
Because I
buildings,
looked
right?
at it that it will actually be very difficult for a place where there is no easy access to water. And the obvious truth is that a place where there is no easy access to water tends to have forests that are more dry because there is no water. So automatically it will be dry. And once it is dry, then it will now be more susceptible to catching fire because the volume fraction will not be having plenty moisture to fight against fire igniting. So such places should be put into consideration by government or people that have like, I don't know, if there's a way to create some devices to be planted in such places to absorb fire kickstarting automatically or something, that would be the best way for, based on my own thinking, to kind of suppress that. Because obviously nobody lives in the bush, and this can happen anytime, except the forest firefighters or those that study forestry, that probably they'll have their offices around such places. But again, they won't be there 24 hours the way they will live in their own homes, in urban centers or in cities, to see the effect of domestic fire and tackle it immediately.
So on buildings, they have the lightning rod, right? A big piece
Yeah,
of
that's what I was
steel,
trying
and
to remember.
it's
Yeah,
grounded, right? So are you
yes.
thinking like lightning rods in the forest that would be higher than the trees, and it would divert the lightning away
Yeah,
from the tree?
yeah. I was just thinking of something like that, or even buried on the ground or somewhere, so that once it feels the sensation of heat or fire about to ignite, if we quickly absorb it from taking place.
But you're not sure how that would happen yet. You're not sure how that would work. But you
I'm not sure.
but so are you working with the idea that that you're not going to get the right answer until you ask the right question? And so maybe you don't have the answer yet, but you're working on getting the right questions.
Yes, I have it in my mind, something like that, because I just discovered that wildfire spread does not have control measures as domestic fire. And the simple reason is that the impact of it is not felt directly or immediately when it happens,
I said,
but it causes a lot of destruction to ecosystem, to climate, to wildlife, to reserve material somewhere inside the bush or some other things, that the cost will be huge if those things are destroyed.
sure. When you say it impacts the ecosystem, some people would say that fire is part of the ecosystem.
Yeah,
That
that should be
it's
true.
not like you have the ecosystem and then there's fire. Like fire has always been a part of the ecosystem.
That should be true because fire is a natural phenomenon. It will come, and it could be through human or natural. So if it is natural, it's part of ecosystem, because even the ecosystem is natural. So
Are humans unnatural?
and humans are natural. So yeah, yeah.
So let's talk about the interface. You talked about domestic fire and wildfire.
Yeah.
Well, now there's a lot more transition between them, right? That a wildfire moves towards an urban area and then becomes a conflagration, where now it's a big urban fire, structure fires. And then you have structure fires that occur in wilderness areas that become wildfires.
Hmm.
So it's hard to separate. You can categorize them by the fuel type, right? By what's burning at the time.
Yeah.
But sometimes these things ignite each other.
Yes.
Pretty complicated.
A bit complicated, actually.
Yeah.
I think domestic fire should be based on fire type, should be like probably buildings,
Yes.
woody material, furnitures. Basically not like tree types or bushes or something. I think
Right.
can be classified as domestic fire.
But we know that trees are very flammable, right? We could see that in a wildfire. So
Yeah.
why do we make our houses out of fuel?
It depends at times, because in some places, some persons now, they tend to roof their houses with steel, like with a metal iron
Yeah.
roof,
Yes.
not woody roof, just to
Right.
avoid the case of fire, because iron cannot burn. It can only get hot and
Right.
be red, and probably once it is hot like that, it can melt if it is being heated, because it has property of malleability. But nobody will be there to heat it to be malleable. So it will just be hot, be red. As time goes on, it will come back to its normal shape and not be hot again. So some persons now use iron to roof their homes. Some use iron doors now, not woody doors, all in the name of trying to prevent the escalation of fire when it occurs. Because once you have a roof made up of wood, you have your ceiling made up of wood, you have your doors made up of wood, you have your tables and the chairs made up of wood, you have a kitchen close to your house, outside the flat or whatever, made up of wood, you're cooking with wood, automatically you turn your house to be a susceptible forest. Because
Yes.
once fire ignites, all of these things are capable of just burning instantly. And you can't use a wet wood to roof your home. It has to be a dry wood. You can't use a wet wood or tree to make a door. It has to be dry.
Right.
So I think, well, they are interconnected. Let me just
Yeah.
use
Right. I
that
mean,
language.
there are chemicals you can spray onto wood that absorb into the wood that make it much less flammable.
Yeah.
Tripotassium citrate or other chemicals, right? You wet the bottle and you spray it on there, and then it dries, and then the wood is much less flammable.
Yes,
So
it happens.
I
Yeah,
think,
that makes me recall in my place. At times, if you want to really roof a house, there's this oil, black in nature. They will spray the oil on the wood against some insecticide that will end up destroying the wood and probably make the wood more stronger.
yeah.
I think something like that.
So when something is less flammable, let's say we take our wood that we're going to build our house with, and then we spray it with a solution that absorbs into it, and then the water dries, and then it leaves a chemical in the wood that makes it burn less. How do you model something like that? If we were to take that back into your part of the world of modeling the fire, what happens in a model that would illustrate how a fuel becomes less flammable?
Automatically, that will come under CFM, that is combustible, because it's also combustible. Even at that point, it's combustible, but not on a fast rate. So I can just create an equation having volume fraction of dry organic substance. I can make it, let's say, alpha 1, and then volume fraction of dry organic substance, alpha 2. Then for that equation, with the incorporation of some chemicals being added, which I will represent mathematically, either having some representation for them, and then I will add it to that equation. So the equation will be the same with the first one as volume fraction of dry organic substance, but with the addition of an extra term to account for this chemical that is spread on this wood.
Okay. So,
Yeah.
so that shows up in your equation just as a time factor, that the fire spread would be slower, and that the ignition temperature would be higher.
The ignition temperature, like for the two volume fractions, if the ignition temperatures are the same, then automatically the one that does not have any chemical being applied on it will catch fire faster.
Yes.
Compared to the one that has chemical on it. So if we are considering both under the same temperature, then by this addition or the incorporation of a chemical into the one we are trying to make less flammable, then that will not catch fire as expected compared to the one that does not have such chemical. And once we run our simulation or we solve our model, then we should be able to see that at the same temperature, varying this parameter, the one that has chemical applied on it should have less burning rate. Else, what we have incorporated is not correct, or maybe it's not done well.
Okay. So I know there's a lot of research on molecules, right? And what chemical will do what, and then sometimes using AI, they would figure out what properties does a chemical have to have in order for it to be a fire inhibitor, and then it would invent that chemical. Right. So are you able to model the impact of different size and shape molecules on how they would impact fire spread? And would that then allow you, instead of trying to test 1,000 different chemicals and see which one slows the fire down, can AI help you predict which chemicals are going to be most likely to slow the fire spread?
I think that would be like a further research for me to work on.
Okay. Now you just need some more money for that, huh?
Yeah.
Wonderful. Well, Abraham, I want to thank you so much for joining me today.
Thank you so much for the opportunity to have a chat and to talk about wildfire problems and solutions and everything. I'm grateful.
Thank you so much. And the research you're doing is fascinating, and I look forward to following and seeing what becomes of the work that you're doing and the new directions that your work goes in as you progress through it. So thank you so much for taking the time to share that with me. Abraham Zhiri from
Correct.
Cambridge. Thanks so much for joining us, and thank you all for joining us here on The Fire Break. I'm Steve Wolf. The Fire Break is sponsored by Team Wildfire. Thanks for listening, and we'll see you at the next one.
Thank you so much.